One of the most effective ways to illustrate Newton's laws of motion was developed by English mathematician George Atwood in 1784. His device, a simple machine which now bears his name, tests the motions of masses under a constant force. The so-called Atwood's machine is the arrangement of two masses connected by a string and hung vertically over a pulley. Obviously, we are interested in the case where the masses are not identical. We want to know how one pulls the other, so we will assume that one of them is bigger than the other. Let's say that M1 is bigger than M2, so we know that when we release them, M1 will accelerate downward, pulling on M2 and making it accelerate upward. And the question here is, what is the acceleration of the masses? Now, before we start writing equations, we want to note the following. 1. There are two bodies, so you need two sets of equations, one for each body. 2. The bodies are connected, so there must be a way in which the equations connect as well. Since what connects them is the string, we should carefully examine the string first. Strings of this type, negligible mass without deformations and restoring forces, transfer forces equally to every point on the string. If you hung a weight and measure the tension on the string, it will read the same amount of force, no matter where on the string you place the measuring device. It is this fact that will connect the equations for both objects. Both ends of the string experience the same tension force, which we will call T. By the way, the pulley also experiences T at multiple points, but we are not concerned with the pulley at the moment. There is another connection to be mentioned. Since the objects are connected by the string, when one moves a distance, x, the other covers the same distance, and they do it in the same time interval. This means that their velocities are the same, and if they change their velocities in the same way in the same time interval, then by definition their acceleration is also the same. So whatever equations we will formulate for each object, we will have the same tension and the same acceleration for both objects. Now we are in position to start writing the equations. So if we look at M1, we see only two forces acting on it. One is the tension pulling upward, and the other is its weight pulling downward. Since we already agree that this mass will accelerate downward, then we know that the force pulling downward must be greater than the force pulling upward. Since it will be accelerating downward, it will make sense for us to use a coordinate axes with positive vectors pointed downward. The total force then will consist of the addition of forces, which is the positive weight and the negative tension. And according to our friend Newton, this total force must be equal to the mass times its acceleration. This is one equation that we get from one object. Now, let's move on to the other object. For M2, M2 moves upward, so the force pulling upward will be greater than the force pulling downward. In other words, the tension here is stronger than the weight. Since this object accelerates upward, it makes sense for us to pick a coordinate system where upward means positive. Here, the total force is the tension minus the weight, and that should be equal to the mass times the acceleration. Now, we have these two equations with two unknown variables. This should not be difficult to solve for you. You take one equation, let's say the one for M1, then you solve for T and use that value for the other equation. After all, that T and this T are the same. We arrange the equation to solve for A. Now we factor A, and you might as well do it for G. We can divide by M1 plus M2, and here we have the magnitude of the acceleration. Now, how do you know what you are doing is correct? You know, sometimes we make mistakes in the algebra, and so how do you know you're on the right track? The easiest way to check that your answer is making sense is by replacing some numbers for which you already know the answer. For example, if m1 is 0, then m2 should be free falling at g, 9.8 meters per second square. This is exactly what you get. Notice the negative indicating the direction. Remember that we chose for m2 a coordinate system where vectors pointing upward were positive. And if m2 is 0, then m1 should be the one free falling at g. And that is what we get. Notice the positive in this case. That is because for m1, we chose a coordinate system where vectors pointing downward were positive. Another thing I need to mention is that you could pick any coordinate system. Let's say you pick a coordinate system for m1 with positive vectors pointing upward. The direction of what it means to be positive does not really matter as long as you are consistent. One does not need to stop there. You can replace that acceleration into any of the original equations to find out what the tension is. Okay, think you've got it? Let's walk quickly through the steps. We can turn the first term into a fraction with the same denominator by multiplying and dividing the same factor, m1 plus m2. This g can be factored and everything else stays inside the parentheses. Now we can multiply this inside here. Everything goes into one fraction since now we have the same denominator. m1 squared cancels and we have 2 of these m1, m2g. And how do you know you were on the right track? Again, you test your result with values that can produce situations that you already know. For example, if m1 equals m2, then the masses should be in equilibrium. And if you look at m1, you should see that in that case, T would equal m1g. This is how you check your answers. You should always double check your work to make sure your calculations are correct.